Let's try this one. We're going to find the area under the graph of f of x from a to b, where f of x is a piecewise function. So the first piece is x, and that's when x is less than or equal to 2. And the second piece is 2, so our function f of x is equal to 2 when our inputs, when x is greater than 2. And we're looking from a equals 0 to b equals 4. All right, so we have the graph of our function here, graphed out. So this is f of x. And we're interested in the region starting at 0 and going till 4. So starting at 0, well, that's right here on our graph. So we're starting there. And then going to 4. And so we're going to calculate this area. It's the area under the curve extending from x equals 0 to x equals 4 and above the x-axis. All right, so let's see how to do this. And just a quick note, when we write this out, or when we look at this, this function is continuous. We can tell that from the graph because these two different pieces, they meet up at x equals 2. So you could use limits to show that it's continuous. And we see that it's non-negative on that interval from 0 to 4. And so the graph, it's non-negative means it can cross the x-axis. It does go below the x-axis. So once our inputs become negative, less than 0, the graph of this function does go below the x-axis. But we're only interested in this section between 0 and 4. So in that section between 0 and 4, the graph is either on or above the x-axis. And that's what it means to be non-negative. And so just a quick little note there, that our function does actually, it's continuous and non-negative. All right, so then the area calculation, to calculate the area for this region, all we have to do is integrate from 0 to 4 our function. Now the issue here is, how do we integrate a piecewise function? This might be the first time we're seeing something like this. And so what we notice is that our piecewise function, there's two different pieces of our function, splits at x equals 2. So we can tell that by looking at these inequalities. When x is less than or equal to 2 and when x is greater than 2, the formula for our function is different. So what that means is, because we're integrating from 0 to 4, and because the piecewise function splits up inside that interval, what we have to do is we have to split up this integration. So we're going to integrate from 0 to 2, our function, and we'll add to that the integral from 2 to 4. So this is one of our definite integral properties. If we're integrating from 0 to 4, we can integrate from 0 to 2, calculate that integral, integrate 2 to 4, and it should be equal. So what we're doing here is we're splitting the integration. And that's because our piecewise function splits at x equals 2. So that's where we kind of broke this up into two separate definite integrals. All right. So now we actually want to fill in what our function is. So for this first definite integral, we're looking at our function f of x from the interval from 0 to 2. So we're looking at this function over the interval from 0 to 2. So here, this is, if we're looking at x values that are between 0 and 2, well, that means x is less than or equal to 2. So that means we're going to use this top piece. Now over here, for this definite integral, we're looking at x values that are between 2 and 4. So that means we're going to use this other piece of our function, x greater than 2. So we fill in these two pieces of our function where they need to go based on the x values for these definite integrals. So this first definite integral is going from 0 to 2. So those are the x values where x is less than or equal to 2. So we're just going to rewrite our function. So f of x is x in that case. And then we're going to have the integral from 2 to 4. And so if our input values are from 2 to 4, that means we're dealing with inputs that are really greater than 2. So what happens when x is greater than 2? Well, we just have a constant function. So we're going to integrate just the constant function 2. Okay. Well, now it's all set up and we can just integrate. So what's the antiderivative of x? It's 1/2 x squared. We'll evaluate that from 0 to 2. What's the integral of a constant? Well, it's just the constant times x. And we'll integrate that. We'll evaluate that from x equals 2 to x equals 4. And then just go through and do each of these evaluations. So this first one, we take the top number, plug it in. We get 1/2 times 2 squared, which is 1/2 times 4, which is 2. Plug the 0 in, and when we plug 0 in, we get 0. So this 2 here comes from doing this whole evaluation. Then we want to evaluate this. So the next portion, so take the top number, plug it in, we get 8. Take the bottom number, plug it in, we get 4, and we subtract. So doing this evaluation gives us 8 minus 4. And if we wanted to, we could really say 2 minus 0 here. Although the 0, you could probably just do that in your head. And so if we do the arithmetic here, we end up with 2 plus 4, which is 6. So the total area for this shaded region is 6. Now, we went through and did the calculus here, but these shapes aren't too complicated. This function, the top section here, our curve is not too complicated. And we actually have some kind of easy geometric shapes that we can just calculate the area of directly if we wanted to. So kind of a more geometric approach here, a little bit of geometry, is, well, let's break this apart. We see that at x equals 2, something kind of, the function's changing. So we really have a triangle. And then over here, I don't know how this is going to look. And then if we look for x greater than 2, we have a rectangle. We have a square. So we have this triangular region here. I can do it. I can draw a triangle here. Sure. And then we have a square over here, a rectangular region over here. We can calculate the area of those. So what's the area of this square? So the area is the area of our triangle plus the area of our rectangle. And the area of this triangle is 1/2 base times height. So the base is 2, the height is 2, 1/2. So 1/2 base times height is 2. And what's the area of this rectangle here? We'll just count up the number of squares inside. So there's 1 square right here, there's 2 squares, there's 3 squares, there's 4. So the area of that rectangle is 4. And so you end up with the same calculation, 6. Same value there. So, sometimes if the shapes aren't too bad, you might be able to use a little geometry and calculate the areas that way. All right, so we've seen a couple examples now involving functions that are non-negative, so above the x-axis. we want to start exploring what happens. We're still going to be interested in this definite integral, but what happens if the function goes below the x-axis? That's what we're going to see next.